Okay, so what we were talking last time? Last time we were talking about supremum infimum. Right, so all of you understood definition of supremum infimum. Definition of supremum infimum is clear. Okay, and I have already shared with you a PDF for this chapter, first chapter, and you can go through the PDF. You can solve the exercises mentioned there, right? And we spend much time on sufficient time on definition, so I think there should not be any confusion or on supremum and infimum, right? And okay, so what is the completeness property of real numbers? If A is a non-empty subset of R, if it is bounded above, it has a supremum in real numbers, right? It has a supremum, means supremum exists in real numbers. If set is bounded below, then it has infimum. If set is bounded, it has supremum as well as infimum. So what we discussed, supremum of a set, right? So which is called as least upper bound, infimum of a set. What it is called? Greatest lower bound, or GLB. Here LUB. So least upper bound, greatest lower bound. So least among all upper bounds and greatest among all lower bounds. So that is what the simple thing about supremum. So if this is my set A, and basically we are talking about A is a non-empty set, right? And why non-empty, that also we discussed last time. So if A is a set, then all these are upper bounds, right? So these are all upper bounds of set A, right? So this is my set A from this to this subset of real numbers, and these are all lower bounds, right? So all these are lower bounds, but least among all upper bounds is what? Supremum. And greatest among all lower bounds is infimum, right? So this is what we discussed. So is it clear?
Yes, sir.
Right.
Yes,
Now we'll uh, try to understand some equivalent ways to look at supremum and infimum. So let A be a non-empty subset of R. Suppose A is a non-empty subset of R. Now let U belongs to R be an upper bound of A. Then following are equivalent. So A is a non-empty subset and U is some upper bound of A. Then following statements are equivalent. Equivalent means same meaning. So U is supremum of A if B is any other upper bound of A, then V is less equal, then U is less equal V. Third, if W is less than U, then there is X belongs to A such that uh, W is less than X less equal U. Fourth, if W is less than U, then W is not an upper bound of A. Fifth, if some positive epsilon we take, then U minus epsilon is not an upper bound of E. That means this is equivalent to if epsilon is positive, then there exists element of set such that U minus epsilon less than X less equal U. Okay, so do you understand meaning of all these 6 statements?
Yes, sir.
So what I am saying is U is upper bound, then U is supremum. Supremum means what? Least upper bound. Supremum means what? Least upper bound of A is equivalent to saying that if there is any other upper bound, it is greater equal V. That is by definition, right? This is obvious from the definition. So what is the 1 implies 2 is clear. Now what is the meaning of this theorem? All are equivalent. All following statements are equivalent means what? 1 is equivalent to 2, that means 1 if and only if 2, 2 if and only if 3, 3 if and only if 4, 4 if and only if 5, 5 if and only if 6, 6 if and only if 1. So if you prove that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 6, and 6 implies 1 means all are equivalent. So what is the strategy? So strategy of proof is, so we should prove that 1 implies 2, 2 implies 3, right? 3 implies 4, just implies, you just prove implies, 4 implies 5, 5 implies 6, and 6 implies 1. Ultimately, if you look at the combined effect, what happens? If you look at the combined effect, all are equivalent. That is the meaning. And proof is straightforward, right? If U is supremum, then you look at any other upper bound, it is greater equal. This is by definition, right? And why 2 implies 3? If you look at uh, any, suppose U is a supremum or any other upper bound, any upper bound is less equal, uh, greater equal U. That means if you look at W, W cannot be upper bound. W cannot be upper bound means what? Right? If any other upper bound, if suppose we assume 2 and we want to prove 3 from using 2, so what we can do? Suppose any other upper bound is greater equal U, and if W is less than U, then W cannot be upper bound, because by 2 any other upper bound is greater equal U. So W is not upper bound means some elements of set are greater than W, so there exists X. So that is what the meaning. This is just interpretation of definitions. So this is exercise, so write down the proof. Right, so this is exercise, write down the proof. And I have mentioned this proof in the PDF also. So all of you got the PDF?
Yes, sir.
And I have explained the proof in that PDF, so you can refer PDF also. and you write down on your own also, because this is just interpretation of definition of supremum, right? If you take w less than u, then w is not upper bound, means u is the least upper bound. That is what meaning is. Or if you take any epsilon positive, and if u is there, and then u minus epsilon is less than u, and this cannot be upper bound because u is the least upper bound, so there exists x inside. The same thing in other words, right? So just interpretation. So is it clear? Is this clear?
Yes, sir.
Yes,
Right.
sir.
So if you understand the definition of the statement in of the theorem, then you can easily write down the proof, right? But these interpretations are very essential while proving supremum or infimum of some sets, right? So therefore you need to think about these interpretations. The meaning of all these statements is same, that U is supremum. Now another theorem about infimum. So let a non-empty subset of R, U is a lower bound of A. U is some lower bound of A, but when it is infimum, so then following are equivalent. Are equivalent. So what is the meaning of statements are equivalent? Because what is my first statement in this theorem? Ki U is a supremum, is equivalent to this. Second, it is equivalent to saying that 3. It is equivalent to saying that 4. It is equivalent to 6. It is equivalent to 5. Means what? If you prove one of these, then that is ultimately the uh, proving that U is supremum. Similarly, what are the equivalent statements for infimum? So U is infimum of A. Now, can you tell me what is the corresponding second statement, which is equivalent to this infimum? If
Sir,
V is any other lower
V,
bound of A, then V is less.
right, any other lower bound of A, when I am saying ki, since I am saying that V is U is infimum, greatest lower bound. If V is any other lower bound, then V is greatest. That means V is less than or equal to V, right? What is the third corresponding statement? What is the third corresponding statement? This is U, and U is the greatest lower bound. That means no number greater than U is a lower bound, right? This is the greatest among all lower bounds. That means all other lower bounds are here, and this is greatest lower bound. So if what? W is greater
W
than,
is greater than
then
U.
W is not a lower bound of E. This is equivalent to saying that if W is greater than U, then there exists X in A such that there exists X in A. So why W is not lower bound? What is the meaning of W is not lower bound? If W were lower bound, all members of set would be greater equal W, but that is not happening, means W is not lower bound, means some elements of set are less than W, right? X is less than W, correct?
yes, sir.
Right. Now for any positive epsilon, U plus epsilon is not a lower bound. Am I right?
Yes, sir.
right? Because if we in U, if you add some positive amount epsilon, then it will be bigger quantity. But we are saying that U is infimum, the greatest lower bound. So this number U plus epsilon cannot be lower bound because the U is the greatest among all lower bounds. So U plus epsilon is not lower bound of A, and it is equivalent to saying that for any epsilon there exists X in A such that for any epsilon U plus epsilon is not a lower bound. That means there exists X such that right now the picture is clear how these statements are equivalent.
Yes.
Right, so very good. Now I will leave this proof for exercise because you have to just sit down and think about the definition and try to write down the proof. Right, then this will help you to understand the supremum infimum in detail. Right. Anyway, so but sometimes our sets are very difficult, complicated sets. So how to prove that some number is a supremum or infimum of that set? Right. So and so this completeness property is LUB axiom. LUB axiom means it is axiom, right? This is assumption. Ki whatever subset of real numbers you take, if it is bounded above, supremum must be there. So in that way, real numbers are constructed, right? People found that some sets do not have supremum, they added them. That's why the system of real numbers becomes richer and richer. So we get the complete set. That's why it is a complete. Right. So, for example, if we want to observe the sets like 1 plus minus 1 raised to n upon n, and n is in the natural number. So, this set is not easy to observe, right? Little bit complicated set. Then, what can you say about supremum and infimum, right? So, if I try to write down elements of this set, what is the first element of this set? What is the first natural number? 1. So, what is the first element?
0.
0. Very good. What is the next element?
3/2.
3 by 2.
So what is the next element? 1 minus 1 by 3, right? Which is 2 by 3. Then 1 plus 1 by 4, which is 5 by 4, and so on. These are my elements. All elements are non-negative. But if you look at these numbers on real line, then first is 0. What is second? Second is 1 plus half, right? 1 plus half, that is 3 by 2. What is third? 1 minus 1 by 3. So here, right, 1 minus 1 by 3. So third element is on left side of 1. What is the fourth element? 1 plus 1 by 4. But what is the second element? 1 plus half. That means in 1 I am adding half. In fourth element I am adding 1 by 4. So where is the position of 5 by 4 now?
Less than
Between
3.
1 and 3 by 2.
Very good. So it is 5 by 4 because we are adding smaller amount to 1 next time. And here I am adding the 1 by, I am subtracting 1 by 3. So next element is 1 minus 1 by 5. So I am subtracting still smaller amount. So here 2 by 3 and here 1 minus. So 5 minus 1, 4 by 5. Right. So ultimately what is happening that you can observe on this line. But which is the larger element, largest element? Afterwards everything is less than 3 by 2 and everything is greater than 0. So we observe that this is observation, right? What could be the supremum of this set?
3 by 2.
3/2.
Right, this is observation, and the infimum is 0. This is observation, but can you give me proof? Can you give me proof? Right, so how to prove it? How to prove this?
So we can take two cases. First one is n will take even and n will take odd.
You can make simple cases, that is fine, not no harm in doing that, but basically suppose we want to prove that, to prove supremum of A is equal to 3 by 2. Right, so first when we want to prove something is supremum, what is the first step? 3 by 2 is an upper bound of A. Right, this is the first step. Prove that it is the first step. It is upper bound. Why it is upper bound? We understand why this is upper bound. For
Sir, because as the n increases, the value of the given expression goes on decreasing, and 3 by 2 is the highest value that we obtain.
for every natural number n, what is basically happening? Ki minus 1 raised to n upon n is less than or equal to half. Is it true?
Yes, sir.
Right. So very good. So minus 1 raised to n by n is less equal half. For example, n is equal to 1, it is minus 1, definitely less than half. If n is equal to 2, then it is half equal exactly. If n is equal to 3, less than, n is equal to 4, less than. So this is true. Fine. Therefore, for every natural number n, 1 plus minus 1 raised to n upon n is less than or equal to 1 plus half. Right? Is it true?
Yes, sir.
Right. What does it mean? For every n, such element, for every n, such element is less than or equal to 3 by 2. That means every element of set A is less equal 3 by 2. That is, for every x in A, whatever member of set you select, because what are the members of set? Members of set are of this type, right? And so whatever n you select, every time you look at the member of set, x is less than or equal to 3 by 2. Correct? What is the conclusion of this? What is the conclusion of this?
3 by 2 is upper bound of set.
Right, is an upper bound of A. Now, one of the observation is, note that 3 by 2 is a member of A. Correct? Is 3 by 2 member of A?
Yes, sir.
Right. And at several steps, I am writing a question mark why. So you need to think when you read later on or every time. So sometimes you believe that this is true, but why that reason you think about it every time. So because for n is equal to 2, it is a member of set. Therefore, how to prove that 3 by 2 is supremum of A? So this we want to prove. Why? Now we go to the our previous theorem. What is the previous theorem? If some number is a supremum, then you try to check any one of them. Right? Try to verify any one of them. That is sufficient to say that it is supremum. So, which is how to believe that 3 by 2 is supremum? So, if you go back 3 by 2, right? So that means if I select any w less than 3 by 2, then it will not remain an upper bound. So that means this is a least upper bound. That means LUB of A. So that means if we select any w less than 3 by 2, then w is not an upper bound of A. Why? Is it true?
Yes, sir.
Because since there exists x is equal to 3 by 2, which is a member of set, such that 3 by 2 is greater than w. That is what the simple reason, and that is why 3 by 2 is a member of set that helps us. If 3 by 2 itself is a member of set which is greater than w, so you cannot go below 3 by 2. So no number smaller than no number greater than we cannot go above we cannot go below 3 by 2. So if you go below 3 by 2, there is a number greater than that which is a member of set. So no number smaller than 3 by 2 is a upper bound. Okay, what is the conclusion? So 3 by 2 is actually least upper bound of A, which is supremum of A. Okay, so this is clear. Any confusion in this?
No, sir.
Right,
No,
very
sir.
good. So what is secondly we want to prove? To prove that infimum of A is 0. Now do you understand? It is straightforward to prove, right? 0 is lower bound. Second, first step is prove that 0 is a lower bound, and second step is 0 is greatest lower bound of A. Now why 0 is a lower bound? How will it?
So because every element in A is greater than equal to 0.
But you need to give some proper arguments, right? So note that,
We'll consider an expression 1 minus 1 raised to n upon n, and it is always greater than equal to minus 1.
right? Right. So for every natural number, for every natural number n, minus 1 raised to n upon n is greater or equal minus 1. Is this true? Right. Therefore, for every natural number n minus 1 and minus 1 raised to n upon n, so this quantity is bigger, right? But if I add 1 on both sides, what I will get? Is it correct? Is this correct?
Yes, sir.
And so every such element is greater or equal 0. So what is the conclusion? For every x in A, every member of set, x is greater or equal 0. Therefore, 0 is a lower bound. And why it is the greatest lower bound? So 0, if I take some z greater than 0, so if z greater than 0, then z is not a lower bound of A. Do you understand why?
Yes, sir.
So why z is not lower bound? Because there exists x, which is 0 itself is a member of set. Is 0 member of this set?
Yes.
Right. Therefore, 0 is not lower bound because there is a member of set which is 0 itself, which is less than z. Right. Therefore, 0 is the greatest lower bound is infimum of A. So, in this case, what was the easy? What was advantage in this particular example? Ki 0 supreme and infimum are actually members of set. That's why our job was easy. Ki if you choose any number smaller than 3 by 2, immediately 3 by 2 is a bigger member of set. Or if you choose anything greater than 0, then immediately 0 is a member of set which was less than that z. So that's why we can declare, we could declare that 0 is infimum. Right, but in some cases, this may not happen. Right. For example, if we take set like 1 plus 1 by n, n is natural number. So, by observation, you can tell me something. What is a supremum? Right. By
2.
observation, you supreme is 2, and what is infimum? See, just think about here, suppose 1, and I am now looking at elements of this. So n is equal to 1, I will get 2. N is equal to 2, what I will get? 1 plus half, right? Then 1 plus 1 by 3, right? Because I am adding 1 by 3 to 1. So left to this 1 plus 1 by 4 and so on. So ultimately, if I am I increase my n, then ultimately where I am going towards?
Towards 1.
Towards one.
I am tending towards 1. But when I will reach to 1?
When
N
n will
becomes
be
infinity.
infinite.
We cannot reach 1.
So this is a correct answer. We cannot reach 1, right? But can you stop at some distance on right side of 1? Can we
No.
No,
stop some?
sir.
No.
No, sir.
So therefore, this is a dilemma because we cannot reach 1 and we cannot stop to the right of 1. So this process is infinite. So when we'll reach 1, so that happens at infinity. But where is infinity? So we don't know where is infinity. It is beyond anything, everything. So it may be at heaven, wherever, doesn't matter. So this is a philosophical fact. So when we'll reach, but ultimately when after infinitely many years, if we keep on following this process, 1 plus 1 by 3, 1 by 4 and so on, when this process will end at infinitely many years, but as a mathematics student, we have that power, we can say that ultimately where it will reach, it will reach to the 1, and that is the infimum. So what is the infimum? Right, so infimum is 1, that is a power, and that we cannot see. In previous example, we could see that 0 is a member of set, 3 by 2 is a member of set, and everything is in between. Right, so that this was our real world. We know the lower bound, we know the upper minimum element, maximum element, but in that case we cannot see we are actually reaching to 1, but as a mathematical power we can say that it will reach to the 1. Right, and that is what we want to prove here. Right, observation is fine, but this is a guess actually. Right, because like in previous example we could see that 0 is there and 3 by 2 is there, but here we cannot see 1 is there. But ultimately we'll reach to 1, that we want to we can see by mathematical power. Do you understand what I am talking about? So this is a philosophical fact. Right, and to understand this fact we need some more power, mathematical vision.
Sir,
Yes.
so as we know that if it is not bounded below, then infimum doesn't exist. But sir, if we see it in that term, then it's not bounded below because it goes on and on.
No. It is not. N is going towards infinity, but the net effect What is the net effect?
Yes.
Right? So to prove that 2 is supremum is easy case because 2 is a member of set, right? But to prove that 1 is infimum is not so easy now. Is it clear? 1 is lower bound that you can easily check. But why 1 is the least upper greatest lower bound? That is not trivial in this case. So for that we need more power. And what is that power? So well ordering property of natural numbers, right? So this is important property or axiom, you can say, well ordering axiom or property. So what is a well ordering property? I think I told this in beginning also, right? If you remember, so every subset of natural numbers has the least element. The statement is clear. Every non-empty subset of natural numbers has the least element. Statement is clear.
Yes, sir.
Right. So for example, you know the set of natural numbers 1, 2, 3, and so on. If I take some subset A, which is uh, 5, 10, right, then 15, and so multiples of 5, I take this. So what is the least element? 5 is the least element. You take any subset of natural numbers, least element definitely exists, but largest element does not exist, right? So if you look at this set, 5, 6, 100, 2000. So this set has least element, but largest element does also exist, which is 2000. Right. So we are not sure about largest element, but least means what? All of you remember the definition of least element? You remember the definition of least element?
Yes, sir.
Right, because it is a member of set and it is least among all the other members. Right. So every non-empty subset of real numbers has the least element. So least element exists. No guarantee about largest element. So this set, for example, all multiples of 5, largest element does not exist. But for this set, largest element exists. So it depends on set, but definitely least element exists. Whatever subset of natural numbers you take, least element exists. So, right? Fine. Is this clear?
Yes, sir.
Very good. So one important property is Archimedean property of real numbers. Archimedean property of real numbers. So what it says is for x belongs to R, there exists n suffix x depending on x. So why I'm saying suffix x? So there exists a natural number nx, right? There exists nx in n. So this natural number depending on x such that n suffix x is greater than x. So what this statements, what this property says, what this property says, do you understand? Given any real number, there is a natural number greater than that. This is a very important property. And this is a consequence of all our previous discussions. The properties of natural numbers and well ordering properties and properties of real numbers. So the meaning of statement is clear.
Yes, sir.
Right? So give me any real number, I can produce natural
So
number greater
so
than
it
that.
can be equal also, no? If we like take 100, then it's equal.
Yeah, but suppose you take x is equal to 100. Does there exist natural number which is strictly greater than 100?
Yeah, 101.
Right. So I will take nx is equal to 101. So there is no harm in saying this greater than.
Yes. Okay.
Right. Very good. So if x itself is a natural number, then definitely there is a natural number equal to, but definitely there is another natural number which is greater than. So therefore this statement is true. Now we'll see the proof of this statement, because this statement can be proved from our previous properties of real numbers and natural numbers. Okay, so let x belongs to R. Fix your x. What we want to prove, given any real number, I can produce natural number greater than. This is a statement we want to prove. Suppose somebody gives you real number x, and what is our claim? So there exists some natural number depending on x, which is greater than x, right? This is our claim. Suppose not. Suppose this is not possible. Right? Suppose we are given some x, and for this x there is no natural number. That is, there is no natural number greater than this x. This particular x, right? We are talking about this x key. Our statement is key for every x we can produce natural number greater than that x. Suppose for this particular x there is no natural number. If we assume this, then we'll get some contradiction, and then we'll accept that there is no such x, right? For which there is no natural number greater than that x. So there is no such x means for every x there is a natural number greater than x, right? Do you understand logically what I want to say?
Yes, sir.
Right. So we are assuming the opposite. There is no natural number. So that is n is less equal x for every natural number. Correct? N is less equal x for every natural. That means all natural numbers are less than or equal to x. Means no natural number is greater than x. So that you tell me what should be my next statement sentence.
An upper bound of n.
Right. X is an upper bound for n, because all natural numbers are less equal x, means this particular x is an upper bound of x natural numbers, right? Therefore n is a non-empty bounded above subset of R. Now you tell me what is my next statement.
N is not bounded above. It is a contradiction.
That we are not, that we don't know right now, right? What we have so far, ki n is a non-empty subset. Definitely it is a non-empty, and it is bounded above, right? See, basically what you are saying ki n is not bounded. Ultimately, we are proving that thing. N is not bounded above. Ultimately, that means n is not bounded above. That is what we want to prove. Ki given any real number x, there is a natural number greater than x. That means no real number is upper bound for natural numbers. That is ultimately the meaning of our Archimedean property. Do you understand? That is what we want to prove actually. Another interpretation of Archimedean property is that n is not bounded above. That means no real number is a bounded upper bound. That is our aim. But suppose every natural number is less equal x, that means x is upper bound. That means n is a non-empty bounded above subset of R. So what is my next statement?
Has a supremum.
Right, very good. Because by completeness property, we understand n is a non-empty bounded above subset of R. So by completeness property, what should happen now?
Supremum of A equals to X.
Then n has the supremum.
N has supremum in R, right? Because what completeness property says, once your subset of real numbers is bounded above and it is non-empty, then its supremum exists in R. So because of these arguments, we came to conclusion that n has a supremum in R. Okay, so let u is equal to supremum of n is equal to supremum of n. Right, so n is supremum. That means what? Least upper bound of n. Then what can you say about u minus 1 by our previous statement of theorem? Is
Not an upper.
not an upper bound of A. Right? Do you understand this?
Yes, sir.
Yes, sir.
Right. So therefore, u minus 1 is not an upper bound because u is the least upper bound, and u minus 1 is not upper bound means what? There exists some natural number m. That there exists a member of set which is what is it? Uh, u minus 1 is not upper bound means there is a number greater than u minus 1. So there exists element of set n, right? There is element m of set n such that, what should I write now?
M is greater than U minus 1.
Right, so u minus 1 is less than m. And remember that m is natural number. So that u is less than m plus 1. Right? Hence, thus m plus 1 is a member of n. Why? Is m plus 1 member of n? Why?
M belongs to n, and if we add 1 in that, it also belongs to n.
By which property? By which property?
Sum of two natural numbers is a natural number.
But we gave some particular name to that property. We discussed this. What is inductive property, right? Do you remember inductive property of natural number?
Yes, sir.
Yes, sir.
Right, so induction. So then, because m is a natural number, so m plus 1 is a natural number and u is less than m plus 1. That means there is a member of set of natural numbers which is greater than u, therefore u is not an upper bound of n. What is a contradiction? What is a contradiction? So everything is in front of you. So what is a contradiction?
We started by considering U as the upper bound.
Right. So we said because of this assumption, ki suppose no natural number greater than x, then we found u is a supremum or u is a upper bound. So this is a contradiction, which is contradiction. to the fact that u is equal to supremum of n. Right. So supremum of natural numbers. Because we came to conclusion that this u has supremum, u is a supremum of natural numbers, and right, with logical arguments again we reach to the conclusion that u is not upper bound. So why we get such kind of contradictory situation? What leads us to the contradictory situation? What leads us to the contradictory situation?
So we took as an assumption that n is less than equal to x for all n belongs
Ah,
to natural.
so we assume that all natural numbers are less equal x, right? There is no natural number greater than x, that we assume. So thus, our assumption that n is less equal x for all n is wrong. Right? Hence, what you can say now, this is wrong. This is wrong means all natural numbers are less equal x is wrong means what? What is the logically? All mangoes in a box are sweet is wrong means what?
There is at least one.
There exists at least one n depending on x such that n is greater than x. Right? There is at least one mango for which the statement fails. This statement fails. Right? So that means there is at least one natural number which is greater than x. Why I am saying nx? Because if I take this is for notation n suffix x, because if I take x is equal to 3.5, then what n I can select? I can select n is equal to 4, 5, whatever. No restriction, right? But if I take x is equal to 10.3, then what n I select? I should select 11 or 12, whatever. But this n is equal to 4 is not suitable for if x is equal to 10 by 0.3, right? So if your x is larger, n must be larger. So n depends on x. So natural number greater than x means it depends on x. So that's why notation. Otherwise, this n suffix x doesn't make any sense, right? Just there is a natural number greater than x. That's important. Okay, so is this clear?
Yes, sir.
Yes, sir.
Right. So therefore, Archimedean property says that given any real number, we can produce a natural number greater than that. So that is the meaning. Now there is another version. So of so here we can say that it is first version avatar 1 and second avatar of Archimedean property. So if x y belongs to R with x positive, then there exists such that nx is greater than y. So this is avatar 2 of Archimedean property. So why I am calling it as avatar 2? Because these two are equivalent. Right. So what it says, given any two real numbers, if x is positive, y whatever positive negative doesn't matter, I can produce a natural number so that nx is greater than y. For example, if I take x is equal to 1 by 10 and y is equal to 52, then what is n such that nx is greater than y? Can you find such n?
Yes, sir.
Right. So can you tell me n in this case?
N will be
521.
greater than 520.
Right. So you just choose any n greater than 520. Right. So I can choose n is equal to 521 or 525. Any number greater than this will work, right? Will serve our purpose. Is it clear?
Yes, sir.
So you look at another x is equal to 1 upon 2020 and y is equal to minus 5000. Then what n you can select such that nx is greater than minus 5000. You choose any natural number now, right, from n is equal to 1, because if y is negative, anything positive is not an issue, right? Do you understand? If I take n is equal to 1, then also it is fine. Nx is greater than this, correct? Because nx is ultimately positive and minus 5000 is negative. Do you understand this? Without any loss,
Yes.
you can directly see. Suppose x is equal to 1 upon 50,000 and y is equal to 20. Then what is n such that nx is greater than y? What is n? You can find it. So you can easily produce this. Do you understand this? So what is our next theorem? Of avatar 1 and avatar 2 of Archimedean property are equivalent. That is, what does it mean? The following are equivalent. So following statements are equivalent. First, for any x belongs to R, there exists natural number n such that n is greater than x. And second, for any xy belongs to R with x positive, there exists natural number n such that nx is greater than y. So these two are equivalent. So equivalent means what? They have same meaning. And when we say that two statements are equivalent means what? First part, to prove. What is our claim in this? What is our claim? What is a claim?
1 implies 2 and 2 implies 1.
Right. If and only if. One implies two and two implies one. So what is the first? One implies two. So one implies two means what? Assume one. Right. So for any x belongs to R, there exists natural number such that n is greater than x. This is our assumption. So what is our claim now? Claim is 2. That is, for any z and w with z greater than 0, there exists n. So nz is greater than w. So for any, right? So we should not use same notation here and here, because I am talking about for every x there is a natural number. So if you take any z and w with z positive, there exists natural number such that nz is greater than w. This is our claim. Right. So let z and w belongs to R and z is greater than 0. So what we want? We want to produce then can I say that W by Z is real number? Can I say that W by Z is a real number?
Yes, sir.
Yes.
And therefore, by our assumption, what is our assumption? This is assumption. Given any real number, there is a natural number. So, what can you say then? By 1, there exists natural number such that n is greater than W by Z. And ultimately, what I get? Nz is greater than W. So ultimately we found that there is a natural number n such that Nz is greater than W because Z is positive. So if I multiply both sides by Z, the inequality remains unchanged. Is it clear?
Yes, sir.
So now second part, 2 implies 1. So assume 2, right, to prove 1. Assume 2 to prove 1. Okay, what we are assuming, that is, given any xy with x greater than 0, there exists n such that nx is greater than y. This is assumption. So to prove for any z real number, there exists n belongs to n such that n is greater than z. So this we want. Do you understand? For any xy, this is going to happen. Now you choose any z. So in particular, if, so let choose any z from real number. If x is equal to 1 and y is equal to z, by assumption what happens? There exists n such that nx is greater than y. That means n into 1 is greater than z. That means n is greater than z. So is it clear now? Is this clear? Because what is our assumption? Whatever x and y, we can produce n such that nx is greater than y. In particular, I choose x is equal to 1 and y is equal to z because we wanted to produce n greater than z. In particular, if I take x is equal to 1 and y is equal to z, then by our assumption, there exists natural number nx such that nx greater than y. That means n into 1 is greater than that. That means n is greater than that. So we are done now. So that is 1. If given any z, we can produce natural number greater than z. Okay, so I think it is time is over. So we should stop here. So any doubts?